Good afternoon. I'm glad to present you part of my work I'm doing between two labs in France, the CRPP and the LCPO, under the supervision of Véronique Schmidt and Valérie Roguez. So today I will be talking about Pickering emulsions, stimuli-responsiveness, and dextran-based. So as a quick introduction, what are emulsions? In fact, they consist in a mix of two immiscible liquids, mainly oil and water. And the one liquid is dispersed into another in the form of droplets. So for instance, in the case of droplets of oil dispersed in a water medium, we will be talking about direct emulsion. And this is the reverse case when we see droplets of water dispersed in an oil medium. These systems are really handy because then, for instance, in the case of a direct emulsion, you can bring lipophilic substances into an aqueous solvent, which can provide saving in terms of toxicity or price. And these emulsions, you can find them in many applications, biomedics, cosmetics, food, paints, or agriculture. However, there are metastable systems because of the large area which is created between two immiscible phases. So to ensure kinetic stability, stabilizer has to be introduced on the surface of these colloids. And to fulfill this purpose, surfactants are widely used in industry. And as an alternative, in the last decades, Pickering emulsion stabilizers have re-emerged. In the beginning of the 20th century, Ramsden and then Pickering discovered that, in fact, solid particles could also absorb at the interfaces of two immiscible liquids and provide long-time stability. And so you can find today in the literature that more and more these kind of systems are studied, and it may even be transferred for the industry. So the use of such stabilizers have many advantages over surfactants, such as the lower toxicity because of the lower amounts of material used, much greater stability over time, and also the possibility to obtain low polydispersity and better size control over the droplets in a repeatable way. Now that we know more about Pickering emulsions, let's talk about stimuli responsiveness. So here it is an oily water Pickering emulsion, so droplet of oil, which are dispersed in a water medium and stabilized at the interface by nanoparticles. In the case these nanoparticles are stimuli responsive, it means that upon the application of a stimulus, which can be various, light, pH, temperature, magnetic field, they can desorb from the interface, which means that the droplets are no longer stabilized and they merge together, we say they coalesce, which ends up with the full macroscopic demission of the emulsion. This is of interest because if you encapsulate active compounds within the droplets, you can then have an on-demand stimuli-responsive release of this active on the target. So these kind of systems are really interesting for many applications in academia or industry, but upon all the systems which are described in the literature, not many of them are interested in the end life of these nanoparticles. Do they accumulate, for instance, here in the aqueous phase, and could they interact with the target? And what about their degradation? Do they degrade at short scale, long scale, or they do not degrade at all? So here lies the interest of our project, is to develop with biofriendly materials which could provide also biodegradability at short time scale, stimuli-responsive nanoparticles able to stabilize Pickering emulsions. So to do so, we developed a full strategy. So starting with upside, we started with dextran, which is a hydrophilic polysaccharide. It's biocompatible, biosourced, and biodegradable by the enzyme dextranase. So first of all, we modified it to provide first hydrophobicity, and then also in some cases stimuli responsiveness. So on the lower left, you can see that for photosensitiveness, we grafted a hydrophobic photosensitive polymer, which is polynitrophenzyl acrylate. On the middle, we grafted acetyl moieties to provide pH sensitivity. And on the lower right side, we grafted alkyl chains, which did not provide any sensitivity, but we take advantage of natural sensitivity of dextranase. So in the third cases, we provided hydrophobicity, which allowed us then to nanoprecipitate those modified dextran chains into stimuli-responsive nanoparticles. Then we verified that these nanoparticles were able to stabilize Pickering emulsions. So in the third cases, direct emulsions, meaning droplets of oil into water. And finally, we attempted the destabilization of this Pickering emulsion with the three stimuli we chose, so light, pH, and enzyme, to verify that first there is a full destabilization of the emulsion, full or partial, and then also that the degradation of the nanoparticles will provide only bio-friendly solutes into the aqueous phase. So instead of just desorbing the nanoparticles from the interface and provide the full destabilization, we provide full destabilization and degradation of the nanoparticles so that no nanoparticulate residue will stay in the aqueous phase. The modification of the dextran chains, what you can see on the upside, we did what we call nanoprecipitation process, which consists in the solubilization first of the chains, and then thanks to a syringe pump, the addition into a non-solvent, which was water, to induce the diffusion of a good solvent into water, and then the precipitation, self-assembly of the modified dextran chains into nanoparticles. So in the three cases, we obtain spherical shaped nanoparticles with a size which ranged from 120 nanometers to 220 nanometers, and in each case, polydispersity index quite low. Nanoparticles, we stabilize Pickering emulsions. So here I will be talking about the result obtained with the photosensitive system. So we varied the amount of nanoparticles from 0.5 to 7 milligram per milliliter of oil, and what you can see is that the more nanoparticles you add in the formulation, the lower will be the size of the droplets, which can be also seen on the graph. The reverse of the diameter of the droplet increases with the amount of nanoparticles, which is typical of Pickering emulsions. It's called limited coalescence, and it's a linear relationship between the reverse of the total diameter, which corresponds to an average diameter, and it's directly proportional to the concentration of nanoparticles. So thanks to this, you can obtain narrow monomodal distribution with great repeatability, because the two parameters are linked, and also you can obtain long time stability, which means that you have emulsions which can last for more than 6 months. So then we took advantage of the light sensitivity of nanoparticles. So where does it come from? In fact, I said in the beginning that we grafted a photosensitive polynitrophenol acrylate polymer onto dextran. So this polymer, upon an irradiation at 365 nanometer, is photocleaved into acrylic acid unit and nitrobenzaldehyde. So it means that when you are applying the stimulus, the wall chain has its hydrophilicity, which is dramatically increasing. So at the nanoparticle scale, it means that light can induce the photolysis of the nanoparticles. So we took advantage of this, study the degradation of the nanoparticles in bulk, and then within the emulsion system. So here you can see an experiment where we presented the spatiotemporal control over the coalescence of droplets, so their destabilization, using UV light. So we put an emulsion into a quartz lamella, and we added a basic aqueous phase, which was found out to be the better conditions for the degradation of the nanoparticles. We covered the half of the plate and the other was not covered. And we irradiated for 30 minutes. And what you can see is that the uncovered area suffered from the irradiation. You can see that the polydispersity increased and the droplets are bigger than the other side where the plate was covered. And it can also be clearly seen with the average diameter of the droplets. So on the left, 169, on the right, 227. So then we tried to use visible light, which was not at all easy, because in the literature you cannot find many examples of visible light to cleave nitrobenzyl groups. But in our case, it worked, so we are pretty happy with these results because it widens the range of application. And in this case, we used fluorescence confocal microscope, and we were able to focus the irradiation in a small area, which is the white dot square here. And as you can see, all the droplets which are colored in blue coalesced into two droplets. So we count them, 21 droplets on the left. So some are outside the box, but it's kind of okay because on the whole sum, it's pretty precise. So this is a good proof of concept for the use of the system as a reactor in a drop for catalysis or biological applications. And maybe, and we can decrease the locus of irradiation to drop to maybe microns and induce the coalescence between two droplets, which is even more interesting. To the results we obtained with pH-sensitive nanoparticles. So we were also able to stabilize Pickering emulsions and saw that the diameter of the droplets decreased with a higher amount of nanoparticles to such a point we call the plateau, where the size did not change with the amount of nanoparticles, which is also typical of Pickering emulsions. But in general, we work in the linear domain, which allowed us to produce in a repeatable way nano-size droplets of oil. We also ensured us that the nanoparticles could be degraded in with the pH. So in this case, the acetals can be degraded in acidic medium, which produces ethanol and acetone as degradation products, which are biocompatible. So it's pretty interesting. And then we did the destabilization experiments on the emulsions. So we used biocompatible oil, which is migliol. And what you can see is that for the control sample, after 5 days, there is still a good stability of the emulsion, which is all creamed, this is a reversible phenomenon. And on the upper side, you can see that after 24 hours, the destabilization of the emulsion is completed. So these nanoparticles are pretty interesting because they can be degraded into biocompatible products such as acetone, ethanol, and dextran, which are soluble in water. And you can obtain an on-demand destabilization of this emulsion within 24 hours in a slightly acidic pH. With the enzyme system, we were also able to stabilize Pickering emulsions. You can still see the linear domain of the limited coalescence. We were able also to induce the partial destabilization of this highly stable emulsion by addition of dextranase in a slightly acidic pH as well. And in this case, the stability of the emulsion were quite striking because more than a year of stability at 37 degrees, which is quite rare. And we were also able to have the delayed on-demand destabilization. So with this system, we pushed a little bit forward our experiments by encapsulating two different fluorescent probes. So one into the oil droplets and another one into the nanoparticles. So what we could see in the confocal fluorescence microscope is the video on the right. Maybe it's not working well, but still you can see that the red probe, which were encapsulated into the nanoparticles, is at the interface of the blue drops, so it it means that we can see the nanoparticles at the interface of the oil droplets. And then the next step will be to encapsulate actives such as kinin into the nanoparticles. So as conclusion and achievements, we were able to synthesize stimuli-responsive grafted dextran polymers sensitive to light, pH, or dextranase, the enzyme. With these modifying dextran chains through the nanoprecipitation process, we were able to produce narrow-sized nanoparticles, which sizes ranges from 100 nanometer to 200 nanometer. These nanoparticles were then used to stabilize oil-in-water Pickering emulsions, and we saw that with the limited coalescence phenomenon, it was possible to produce in a repeatable way narrow-sized droplets. And then for first the nanoparticles, we assessed that they were degraded with the right stimuli. And then on the emulsion system, we were able to induce the coalescence of the droplets and even the full destabilization of the emulsion by applying the right stimulus, so light. We were able to use UV, but also visible light, pH, or enzyme stimuli. So in the three cases, we were able to destabilize on demand the highly stable Pickering emulsion we formulated. So I would like to thank the organizers for the opportunity to present my work. I'm really grateful for this. Thank you. I would like also to thank my two labs and all the people I work with, and also the funding. And most of all, I would like to thank you for your attention. Thank you.